meet down here for lab. Today and tomorrow. Okay, test 3, we will have mass spectrometry. We had IR for test 1, mass spec for test 3. We did not have any spectroscopy for test 2 that you just took. That's the only test that I give in Organic 1 or 2 that does not have spectroscopy. Test 3, mass spec. Mass spec is covered by video only as IR. Today I'll send out the handout that goes with the mass spec video. You should have the handout with you when you watch the video. There's only one video. Okay, I have a handout here. One stack. Okay, let's do dying. I know you've been dying to get this handout, so I give it to you today. Resonance. I saw a cartoon one time that said, define resonance. And the student said, that's where you live. And the professor said, no, that's residence. And everybody laughed. No, this is resonance. Okay, let's pick up here. At the bottom, anybody got the answer? Total number of p orbitals. How many? 10. Yes, 10. Number of pi electrons in the conjugated system. 10. 10 and 10. Bond order for each carbon-carbon bond. For which ones?
Well, they each have a 2 and a 1.
All of them except for the last one.
They're all 1.5. Is that a full double bond?
No.
It's actually not a full double bond because with your resonance structure, each double bond, they're all 1.5 except for the last two. What's the bond order of the last two carbon-carbon bonds? Bond order equals 1 here and here. Those are true single bonds. Neither one of those are involved in any pi bonding. All the rest of them are 1.5. Not quite sure where we left off at. Cations. Yeah, benzylene cat, 2 types of cations. Stabilization by one pair. Did we do this one here?
Yeah.
You stopped at C.
We did the
Stopped
top
at
one.
C.
C.
Did we do this one though?
Yes.
Yes, sir. Noted.
Yeah.
Maybe I did.
We did this one?
They don't like
I have a
that.
question.
I think you told us to do it on our own.
Yeah, go over it.
Did we do this one in class?
I don't work with them.
On our own, yeah.
I'm having trouble hearing.
No.
No. I didn't think we did, but I heard either yes or, I don't know. I don't think we did this one. Let's do this one. Resonance, well, we have a long pair. What type of orbital is that long pair in? That's it. What type of orbital is a lone pair in? Let's do that one next time. We did this at the bottom. Did we do this one here? Answer to this one was one on the right. How about this one down here? Did we do this one?
No.
Answer to this one. Where are you going to make cation at? First off, here's your alkene. Your alkene's in the benzene ring. But this is a magical benzene ring. Benzene rings do not react in this organic one. Never react. They're less reactive than just a standard alkene. Okay? Never react to benzene ring in this class. Next class you will. It requires a little more different type of reagents to react. One alkene, here we go. You don't want to make cation on left or right. On the left. If you make cation on the left, it would look like that there. If we make cation on the right, it would look like that there. Yeah? Which cation is better?
Right.
One on the right, resonance stabilized. What do you call such a cation? Benzylic cation. We did resonance structures up there for a benzylic cation. Charge is delocalized. Does that charge just sit on that carbon? No, it's spread onto some of these other carbons by resonance. I have a resonance hybrid here. This is a fake structure. It's no longer an adequate structure. How about this guy? Does it have any resonance? Yeah, you can do resonance over here, but is there any resonance where you can delocalize the charge? No, there's no p orbital next door. Either that's an isolated cation. Delocalized cation, more stable. More stable cation will form. Then the iodine attacks. Product will be here. So that's the cation that's going to form. And iodine attacks there. So, resonance affects the regioselectivity of these reactions. Anions. Resonance of anions. How do you stabilize an anion? Do we want to move electrons towards it, or are we going to move electrons away from the site? Away. Away. Okay. First, the theory. What type of orbital is this lone pair in? Well, day one or week one, we should have said that anytime a lone pair is next to a p orbital, it's going to want to be in a p orbital, right? You've got to see that. Why did we discuss that on day one, day two? So you can do resonance. Because that's reality. What do we have here? We have p orbital, one electron each making pi bond. Lone pair next door, but it's going to want to be in a p orbital. Why? So it can play the p orbital game and interact and line up. And this is a good thing. Extra pi bonding. What do we see here? We see a conjugated system. The lone pair is said to be conjugated with the double bond. How many p orbitals are conjugated?
3.
Here. How many electrons in the pi system? That dot ended up being right there on the line. 1, 2, 4. 4 pi electrons. Extra electron, that's why it's a negative charge. Well, you can see that anyway, it's a carbon. I don't know if that applies every time. It's a carbanion, it's negative. Because if that was nitrogen, this would still be the same, yet it would be neutral. So it's minus because we see a minus here. Resonance, how do you stabilize the anion? Electrons away from it. Here we go. On our paper on the board, we can start with these electrons. And lone pair that's conjugated is always a great place to start with your arrow movement on your paper. The lone pair is said to be conjugated. Great place to start with moving them. These electrons, okay, I don't think we've done this before. The old in and out. We did the windshield wiper, right? It's the old in and out. These electrons in, but we can't have 5 bonds of this carbon, so we got to move these out. What does that arrow movement give? We now have pi bond here, right? These move in to make pi bond. Another bond, which is going to be a pi bond. These move out here to become what? Lone pair. Now charge. Golden rules of resonance. Every resonance structure should have the same net charge. Right? Here we go. There's a resonance structure. Which one's major, which one's minor? They're the same thing. They're equal contributors. So the hybrid is a perfect blend. Perfect blend. What's the bond order between the carbons on the right? 1 or 2? 1.5. How about on the left? 1.5. Here's your electrons in reality right here. What's the charge on this N carbon? Over here? Here's your resonance hybrid. If you can look at this anion, it looks like this. Which bond is longer, the bond on the left or the right? They're actually the same exact length. A perfect blend of those two. Once we have 3 p orbitals conjugated, it becomes like a garden hose, and then we put electrons in there. If you had a garden hose, would some of the electrons stay over here and none over there? The electrons, the water in the hose will spread out equally through there. And that's the structure that you have here. There's your resonance hybrid. Here's your 2 fake resonance structures, resonance arrow. We have delocalized the charge. When you look at this, do you see charge just on carbon? No, you have to see that. Some of the charge is here, but half the charge is over on the other carbon. A delocalized anion, stabilized by resonance. Down here, draw resonance of this anion. That's the conjugate base of phenol. If there was an H there, it would be called phenol. Some people say phenol. I say phenol. What do you want to call the anion of phenol? What do you call a negative oxygen? What do you call a negative oxygen? What do you call this here?
Hydroxide.
Why so quick with that? So hydrogen oxide, we shorten it to hydroxide. What do you want to call that?
Methoxide.
It's a methyl oxide. We shorten it to methoxide. What do you want to call that one? It's called a phenoxide as the anion. Draw resonance structures of the phenoxide anion. We're using the old in and out method, right? Okay, these electrons can move in here, and these can move out. Your arrows lead the way. Now we draw the result of the arrows. Pi bond here, right? Electrons out. Pi bond here. We now have a lone pair here. That's what I mean by these electrons moved out. That's now a minus. How many lone pairs left on the oxygen? 2. We did not do anything here or here. We can keep going. These electrons can move in here. Make a second bond between these two carbons. These move out. Okay, I can move that bond, which looks like the pi bond. Either one can be the pi bond. Take these, move here. Pi bond here. No change there. Lone pair here. And the lone pair on carbon makes it an anion. We can keep going. These electrons can move in here. My bond is connected here, yeah. These move out onto carbon. If we keep going, these electrons can move here. When we come here, why don't I do this? These come in. That's got 4 bonds. If we make another bond, something has to leave. You can't have 5 bonds. Which way? Right. We would never do this because that's a sigma bond. We do not move sigma bonds when we do resonance. If you did that, you'd be breaking open the ring. Golden rules of resonance. I'm sure the first one probably says, don't go moving sigma electrons. What does it say? Somebody got it? What's golden rule number 1? Only move pi electrons. Move these out, what do you get? You get the charge back where you started. on one of the sheets, Charlie Brown or somebody? Okay, the benzene ring resonance. Let's do that. It's already drawn there for you. Boom, boom, boom. Please just read that little bit there. I did some handwriting on that page. All right, you got these here. Boom, boom, boom. What's the relationship between these two? Let me do this. Let's put two substituents here. One, 2-dichlorobenzene. Yeah. What's the relationship between these two compounds? These are the same exact compound. Because neither one of these is correct in here. The true structure in the ring is a bond and a half all the way around. Both of these are really that there. And a lot of times you just draw the benzene ring with a circle. These electrons, the bond order of every bond here is 1.5. We can get to that by taking these electrons here, moving these here, and moving these here. Okay? So that's, you see the difference? What we ended up with there, the double bond is here. All right? I'm saying it's the same thing. Because really I'm looking at the charge. Resonance structures that involve moving charge is what we're really focusing on. So this anion here is delocalized, thus stabilized by resonance. If we had this anion on the other hand, with no pi bonds in the ring, can you do any resonance here? There's no p orbital in the entire compound. The answer is no, you cannot do any resonance here. That's an isolated anion. Okay. Which one's more stable, left or right? Right's more stable. That's why the OH compound here is more acidic than this one. This OH compound is more willing to become the anion because the anion is so stable. Very important to be able to do resonance with benzene rings. Okay. Resonance in neutral molecules containing heteroatoms, non-carbons. Aniline. You draw resonance structures of it. Now, aniline is isoelectronic to phenoxide up there. They both have benzene ring, and they both have one lone pair conjugated with the benzene ring. That makes them isoelectronic. Now, the oxygen has a negative charge, where the nitrogen down here is neutral. But that's not going to change much at all, other than the same net charge. Can you do resonance structures down here? Is this lone pair conjugated? What type of orbital is in it? P orbital. Anytime a lone pair is next to a p orbital, only be in a p orbital? What do we say about a lone pair being conjugated? Great place to start in drawing your resonance. Anybody have any resonance structure yet? At least one? Anybody got one resonance structure? Seeing issues with charges. Seeing issues with charges. This looks good. I didn't look at the other two. Looks good on the drug plus closer to the nitrogen. On the atom that's charged. Correct charges, correct charges. These electrons move in here, and these out. The old in and out, yeah? Now double bind to N, two H's there. That's a positive charge now. Because it's no longer a standard nitrogen. Move these out, we have lone pair here. Well, that's no longer a standard carbon, and if you do charge, it should be minus. Boom, boom. All resonance structures have same net charge, yeah? What's the charge of, net charge of this? Well, then resonance structure should be net neutral. Is it? Net neutral. All we did is reposition some electrons. We haven't lost or gained any electrons. It still should be net neutral. We can keep on going. These electrons can go here. These can go out. Yeah? Yeah? These electrons can then come here, and these can come out. Pi bond now here. These came out to be lone pair here. And then what if we move these here and move these out? We pretty much get back to the original. Again, the pi bonds will be changed in the ring. Common type of question here. I'm going to redraw aniline. Which carbons of the benzene ring of aniline are most electron rich? You look at your resonance structures. Most electron rich in reality. Well, the hybrid is the reality. The hybrid comes from blending these. I'm not going to draw the hybrid, but we can say, if you look at the hybrid, which carbons would have more minus character? This one would have partial minus. Those three carbons have the greatest partial minus character. We see that from the resonance structures. Isn't that where the minus falls in the resonance structures? Yes. These are most electron rich. That means these have the most electron density in the hybrid. So we just answered this. We could then answer such questions. Which amino group of the two compounds above is most electron rich? Here we have additional substituent added to the ring. Different location though. You need to do this on your own. And you need to draw all resonance structures. We can move terminology. We're moving the lone pair into the ring. We moved it onto the carbon, see the lone pair? We moved the lone pair into the ring. In one of these examples, you can move the lone pair into one of these groups. Or you can delocalize the lone pair into one of these groups. But only in one of these compounds can you do that. The more you can delocalize this lone pair, the less it sits on the nitrogen. Which will be most electron rich? Which nitrogen will be most electron rich? The one in which you can delocalize it more or less?
Less.
Which nitrogen will be most electron rich? The compound in which you can delocalize it more or less?
Less.
Less. Because the more you delocalize it, the more you're putting the electrons other places. Hopefully that makes sense. Like money. I got $100. If I delocalize some of my money to everybody in the world, how much money do I have left? Not much. But if I delocalize my money to just one friend, I'll have more money left because I didn't delocalize it that much. The more you delocalize it, the less electron rich you become. Practice your resonance structures and answer that question. Terminology, understanding what's going on. We're dealing with neutral compounds right here. Delocalization of pi bonds to heteroatoms. Can you draw any resonance of this simple molecule here? We started with a neutral compound. It was a diene. I tried to tell you it was kind of difficult. But it didn't have any polarity. Here you have polarity. Right? Isn't that oxygen pulling? We've got a pi bond. We've got pi electrons. These pi electrons are pulled towards that oxygen. That can help us draw a resonance structure. Okay? We can just move the pi electrons, we can just move them up to coincide with the polarity that we see. What's the resulting structure look like? But what does that arrow mean? Moving them up, and we have now oxygen with how many lone pairs? With 3, and that's a minus charge and a plus on carbon because the net charge is neutral. Is that a resonance structure? All we did is move pi electrons. Yes. Again, it coincides with the polarity that we see here. The electrons are pulled. True structure is a blend. What's the true bond order between the carbon and oxygen? About 1.5. Is it a perfect blend? Which one's major? Which one's major? Who says this one? Who says this one? Why do you say this one? Nikki?
Is it because the oxygen wants to be an anion?
It's a reasonable argument, yeah. What's the argument for this one? Who voted for this one?
Has also more bonds.
More bonds. This has more bonds. Also, there's no charge separation. Charge separation is typically not as good as, all right? That doesn't mean you can't make a good argument for this one, though. You just turn out that there's other arguments that make this the ultimate. This is major. This is minor. But it is a significant contributor. Some of those electrons are pulled. Okay? There's a pinky bond still here, though. Because you want to keep some bonding there. Partial minus, partial plus. If you could look at a carbonyl, if you could look at this ketone, if you could take a Polaroid of it, it would look kind of like that. Both of you are right. Everybody's right. They're both good. But I'd probably say, there's the kid. The kid looks more like this mom. Mom's got more bonds. Looks a little bit more like that one. A hybrid is not always a perfect blend, and here it's not, okay? We said bond in half. It's actually closer to what, 1 or 2? It's actually a touch closer to 2 than to 1, so it's like 1.6 or 7, you know. But we don't get into that kind of a detail. We just say it's somewhere between 1 and 2. 1.5, okay. We would never move these electrons the other way. We would never draw anion here and make that positive. Right? I've already think of 3 reasons why not to do this. First off, this doesn't go with the polarity that's here. Why would carbon isn't going to pull the electrons? What's another reason not to do this? Oxygen doesn't have an octet. What do we say about that? Electronegatives not having an octet? Very bad. They'll hunt you down. They'll make you pay for it. Not going to like that. What's another reason? I can't remember the third reason, but I'm sure we can think of it. No good. Electrons are going this way. What are we doing? We're doing resonance structures of neutral molecules with heteroatoms. Okay? What we just did. Can you show resonance structure of this cation? All possible resonance structures. There you go, one resonance structure. Lone pair from fluorine, conjugated. Did anybody get another resonance structure?
Can you not pull that, don't block from the other?
Yeah.
You mean take it down here
Yes, sir.
and leave this, how many lone pairs here?
2.
What's the charge of this oxygen?
Close.
Does it have an octet?
9. Okay.
Doesn't have an octet. Could be knocking on your door later today.
Baseball back.
Could you pull it up and make the oxygen negative? Like pull it up long enough?
Move these up, make that negative, make this positive. That would be a resonance structure, but it would not be one that involves delocalization of the charge, which usually my questions will say. If this was a carbon, you could do that. Okay? If that was just an alkene, instead of an oxygen carbon, yes, you can do this. Okay? Because carbocations we see them all the time. Carbocation, no octet. That's fine. That's fine. But not for oxygen.
Doesn't fluorine,
Do it?
doesn't fluorine keep being positive though, so.
Yeah, but it's got an octet. 2, 4, 6, 8. As long as it has an octet, it's okay. And fluorine is actually good resonance. Fluorine is better at resonance with carbon than chlorine, bromine, or iodine because it's the same size. The p orbitals are the same size, so they overlap. We talked about overlap before. These are overlapping. Are those overlapping p orbitals? No. What we've not talked about is size. Those two are right next to each other. The overlap is not as good because one is bigger than the other. Fluorine has the same size p orbital as carbon. So that's actually better than if it was a bromine. So that would be a bigger p orbital. Okay? Fluorine is good at resonance. As long as it has an octet, it's fine sharing. You leave a fluorine with no octet, it'll hunt you down. By the way, when I put my eraser in the left hand, that's medical school mode, med school mode. That's how they do it in med school. They write like this. All right? Two-handed. All right, various practice to be doing here. Acid-base chemistry. All right, we had a little resonance with acid-base back then. You can review that and make sure it makes even more sense. Question, Layla?
Oh, so back up there so the ketone is an exception to the rule that lone pairs are typically not conjugated when the heteroatom has a pi bond. That last sentence in the paragraph.
What's your question?
Well, so the ketone is an exception to that rule because the oxygen has a pi bond, but you can still have a resonance structure.
I still haven't. Still don't know your
She's
question.
referencing that last sentence where it says no for the heteroatom. Lone pairs are not typically conjugated.
What's your question about the oxygen?
The first structure that's just the ketone. So would that just be an exception to that
I don't
rule?
know. Exception to what?
To the rule that the lone pairs are typically not conjugated when the...
No, that's no exception.
Then how come you can conjugate the lone pairs with a ketone?
These lone pairs are not conjugated.
What type of orbital are the lone pairs in?
sp2.
What are they?
sp2.
sp2. They're both in sp2. And since they're in sp2, you better not be doing resonance with them because we only do resonance with electrons that are in p orbitals.
Then how come it had the minor resonance structure with
We
the...
took these two electrons, which are in the p orbitals,
Oh,
and we just moved them up, and that's how we got the,
okay,
Keep thinking about it.
okay.
Okay. Why is this so much more acidic than this? We look at the anions, right? This anion called the phenoxide is more stable because by resonance, right? This anion would not be stabilized. Thus, that's more acidic. Why is that more acidic than this? Need to understand why. Need to understand why. Need to be able to understand down here which is most acidic. The nitro group, we'll finish up here. Lewis structure. Double bonded to one oxygen, single bonded to the other. Lone pairs. Typical Lewis structure for nitro group. You'll see nitro group in organic 2. Of course, you have resonance here, so this is really a fake structure. But you can work with this and do resonance. Again, resonance into the ring, but can you do resonance into the group? One of them you can, the other one you cannot. Need to look at that. Then there's questions on the flip side. Okay, you should be able to work through the remainder of this. We'll see what type of questions come up tomorrow on it. Resonance is very important for understanding acid-base. You should look back at your acid-base handout from a couple of weeks ago.